Everybody's having a good time. Sorry to interrupt. It's an absolute pleasure to introduce our speaker today, the Osterberg Lecture, Professor David Muir Wood. He's here for a couple of weeks, so if you haven't had a chance to talk to him yet, we can schedule that. Come find him. He's currently in my office. We're enjoying sharing the same office. And we think, have an office for him someplace else, but we're not using it. So come send us an email, or just come swing by and you can find him there. I do want to first mention, of course, George Osterberg. This is the Osterberg Lecture, named after George Osterberg, who was a professor here at Northwestern for a very long time, and was one of the pioneers in geotechnical engineering, known for soil sampling, soil testing. This is an endowed lecture, so we're glad that we have this opportunity to bring distinguished speakers in. And I'll give the introduction that I left sitting in my office in a sort of a improvised way. Professor Muir Wood really doesn't need any introduction, and the evidence for that, I'll work in reverse, is sitting on the podium up here. He's authored 4 books. He's known worldwide as an expert in mathematical modeling of the behavior of soils, constitutive modeling of soils. He's also known for the development of testing apparatus, and therefore it's extremely appropriate to have him here as the Osterberg Lecture. He got his PhD from Cambridge. From Cambridge, was a lecturer at Cambridge. From there, went to Glasgow University, and after that to Bristol, where he was head of the department and dean at both institutions. After retiring, he went to University of Dundee, moved half-time to Dundee. David is going to correct me if I get any of this wrong. Moved to University of Dundee, where he still holds a fractional appointment. So he's mainly emeritus, but fractionally appointed at University of Dundee at the moment, and is using the opportunity to travel the world. So you would have seen in his bio that he's been lots of different places, and we're thankful that he's now here at Northwestern, visiting us for an extended period of time. So with that, hopefully not overly lengthy introduction, I'd like to get David to give you what you've come here for.
Thank you very much. Thank you. Right, so the title of my lecture today is Particle Continuum Duality, Intermediate Scales in Soils, and I'll show you various ways in which there are numbers which come into the behavior of soil systems which are bigger than the particle size, which might be the obvious particle scale to be using for many problems. But before we get on to that, I usually start off with a brief commercial break. Just to remind you that these books are available, and I'm prepared to sign copies of them if you have them, but they're all very reasonably priced, and they make a very good fitting on your bookcases too. And the 4th book that James mentioned is called Civil Engineering, A Very Short Introduction. It's as part of a series that Oxford University Press have for very small books about very big subjects. And you'll find that probably in most airports or booksellers around the world, you'll find a great sort of stack of these. There are many different titles in this collection, so I recommend that to you as well. Anyway, right. So these are the themes. I know there's a lot of them, but actually it's going to be quite quick for some of these items on the list there. But there's various tools that we might use to look at the formation of localizations or other behavioral effects in soil problems, and we'll see how we get on with these things. So first of all, there's this matter of the particle continuum duality. I mean, it's a fairly obvious thing to say, but it's like the question of sand, which blows in the wind, flows like a liquid, but supports loads like a solid. And it's interesting if you are familiar with your biblical stories of the man who built his house on the sand or the man who built his house on the rock, that actually St. Matthew talks about the building a house on the sand as being a bad thing, whereas St. Luke, who was a doctor, and is much more clued up about these things, he says that it's the man who built his house without a foundation that made the mistake. So he doesn't say that sand is bad, he said that no foundation is a bad thing. I think we would agree with that. So take Luke rather than Matthew as being the guidance on the use of sand as a foundation material. And here's a sort of a little key diagram to show why we're interested in the way in which soils flow as well as settle down. But in general, we've got, let's use the mask perhaps. As engineers, we're usually interested in this region down here where we have the soil staying still, so we have a stasis, and we're looking at small recoverable deformations of these soils under working loads. If you go beyond small deformations, you get large deformations, and perhaps localization or flow, maybe actual transport and flow if you have water around, landslides, dense flow, sedimentation, and it's the structure that is left after sedimentation which actually generates the stiffness and isotropy that we have for our existing soil. So this life cycle here is informative in telling us about how we have got to where we are now and why the behavior of the soil is what it is at the present moment. So the response that we have now is controlled by the fabric is controlled by deposition is controlled by transport. So understanding those various things allows us to think about the way in which the anisotropy of the present soil will be varying depending on what's happened in the past. So what is it about the soils that is special? When I was an undergraduate at Cambridge, we had a series of lectures called on current research topics by the professors around at those days. Ken Roscoe was the professor of soil mechanics, and he would say that, well, structural engineering, they're scraping the bottom of the barrel to find research topics. But in soil mechanics, we are just getting the lid off. There's this exciting stuff inside. And I think we're still, that was in 1970, 1969, 70, so whatever we are now, 50 years on, we're still in the same position of having the excitement of opening the lid, of seeing the magic of the soils inside this barrel. And the key thing is that, what is it that makes soils different and difficult to describe? Well, it's the fact that there's always space in the soil, so that you've got particles and space between the particles, compressible space, and it's that which actually is the key feature of soils by comparison with other engineering materials. So whether you're dealing with sand, or gravel, or shingle, or clays, you can see here the different molecular shapes that we have in these different materials. So there's a lot of space there, a lot of gaps, and it's these gaps which actually make the behavior of soils challenging to describe. So the challenge of soil mechanics is the result of the presence of voids around the particles. And in everything we do with soils, they are aware of this surrounding space. So the challenge in modelling is always to try and accommodate the space as well as the soil particles. And we're generating constitutive models, wherever they might be, and they are this link between stress and strain. It's fairly straightforward stuff, but we're obviously trying to develop these models in such a way as that they will describe properly the way in which space and solid interact in the behavior of the soils. So here is the sort of conundrum that we have all the time, that soil is composed of particles, but we describe it as a continuum in all our analyses. I think we probably have to, and use terms like stress and strain, which are continuous properties rather than properties that are relevant to particulate materials. So one of the questions that we might ask ourselves are, given that we have a particulate material like this, how big is the representative element we should have to describe this material? We're trying to develop this relationship between stress and strain, but what is the area, what is the region that we need to look at to describe this material properly? So soil is composed of particles, but described as a continuum. Stress is force over area, strain is gradient displacement. Are those things relevant at all when we come to look at this particulate material? And the answer is that they're quite difficult to describe. So for analysis, we treat soil as a continuum, but the properties that we're trying to describe emerge from its particulate nature. So we always have this continuum particulate duality to look at all the time. Okay, that's just to remind us, to emphasize the fact that we are looking at this particulate material. Now we can start looking at some intermediate scales. And we'll see that there are about 5 that I've dug out which relate to different aspects of the formation of, the behavior of the soil, and ways in which numbers come in which are not just soil particle size, but actually multiples of soil particle size. So the first one is to do with the sort of mobilization of friction and dilation along a shear band. So you have a material which has, perhaps in a biaxial test, separated along a shear band like this, and there are movements, x and y. X is along the band and y perpendicular to the band. The stresses is sigma and tau. So if we look at the volume change, then there is a region from the peak of the shear stress the softening region down here down to a sort of critical state condition, and a corresponding change in dilation rate. This is volume changing its displacement, high dilation falling to 0. And there is a length of shear band over which these changes occur, so that from high dilation to 0, or from high strength to critical state strength, there's a certain length of band required for that. And you can see it in these tests of Varoufakis. Here's the high stress ratio falling down to a critical state value, and the dilation high and then falling to 0. And there's a sort of length of band which you could I've labelled here L1, which is the length over which the length of the band over which this major change from peak to residual is actually occurring in the material. Well, Varoufakis was looking at Karlsruhe sand. We were using Leighton-Buzzard sand in Cambridge, and we reckon that probably it requires something like 150 times the D50. So the median particle size D50, 150 times that is about the length over which you find the dilation going from high value down to 0, and you find that the strength going from a peak down to a residual value. Well, so there's an intermediate scale of the first order, sort of a mobilization length which might be quite large, 150 times the D50. And this is relevant for modeling of soil problems. If you have a problem which actually is dependent on movement, displacement rather than strains, so you have a failure mechanism which actually requires blocks to slide against each other, then this is clearly going to introduce this idea of a shear band and displacement and this transition from peak to residual along a part of the band. And that's fine so long as you're looking at the problem in real life. But if you have a big prototype and a small model, then in the big prototype, this transition length is going to be quite small by comparison with the overall failure zone. So here's a failure region from the edge of a footing to the free air. And so this transition region is quite short. But in a model, on the centrifuge, for example, you might find that here's the mechanism, and this L2, which is the distance required to get from the residual to the peak, is much more nearly like the whole length of that particular failure mechanism for the material. So for a model, which is where the behavior is dependent on the displacement on a failure surface, you should be concerned about the fact that this length over which these changes occur is a much larger proportion of that failure surface than for the prototype itself. So there are implications of this particular intermediate scale, this very long one, for physical modeling of the material. So that's the first intermediate scale. It's not particle size, it's a multiple of particle size, it seems, and maybe 150 times D50 is about the right length for that. It's quite a long distance. The next idea, these are the sort of subsets of intermediate scales really, is the idea of dilation bands. And I call them dilation bands because the way in which we observed them in those early days was with radiography, X-rays, and what you could see was changes in density. Now they might have been shear bands as well, but I don't know that because all you could tell with the X-rays is that they were points of density change. So I've called them dilation bands here because that's what they certainly were. They may have been shear bands as well. So the various circumstances in which you get those things. Here's a typical picture of a radiographic observation of a shear band, which has occurred because this is a trapdoor problem. This is the part of the basement of this model has dropped by that distance, and as a result of that, you get shear bands forming, or dilation bands, but they're shear bands as well, forming back into the material. This is sand. These black spots are lead shot being used to look at the displacements over the field of the problem. From the displacements, you can estimate the strains. These days, you could probably get a good field of vision with a camera and look at a continuous distribution of strains, displacements using PIV or whatever you wanted to use. But in those days, we were stuck with radiography as being a way of detecting density variations or movements of these black markers. Now, what happens in this case, this trapdoor, is that you first of all get this dilation band, shear band forming, but then as the trapdoor moves further down, so the dilation that you get along this shear band is reducing towards the critical state angle of 0, and so this particular shear band is no longer kinematically acceptable for further movements. So you get B as being a second shear band forming, which is allowing the soil to move down with the trapdoor and to accommodate the fact that the dilation is changing along this old shear band and along the new one as we go on. So as you see with this particular problem, you get A, B, C1, C2, there's a sort of sequence of formation of these various shear bands, dilation bands, as the trapdoor sinks. So the notion here is that the radiography can pick up density variations. The patterns of the dilation bands result from variation in dilatancy, and I've called them dilation bands because they may be shear deformation and shear bands, but I don't know that they are necessarily. Sorry, that's so. And the question raising here is instability in volumetric response leading to clear contrast in density and hence patterns of dilation bands, is it necessarily linked with classical shear localization? Probably it is, but we don't know that. We don't need to know it either. So here's a very simple exercise of trying to work out the thickness of such a shear band in a granular material. This is a very coarse one. It's a gravel of 3 millimeters median grain size. And we have a rotating blade which is rotating into that material. So we push it in, rotating about the top there, rotating it, moving in here. And we measure the movements occurring across this shear band, across these two sections. So here is the movement, horizontal movement of those two, of gravel particles along those two sections. You can see them in a photograph. It's very, very simple to see what's going on, vertical position. And you can see that the track of the movement of these two measurement sections here gives you a very clear indication of the movement above the shear band, where this is rotating around with the wall, and the bottom here where there's no movement at all. And this distance that's like that is something of an indication of the thickness of that shear zone. So we see what we have here is two rigid blocks, one rotating with the wall, and one below that, separated by a zone about 60 millimeters thick, which is about 20 times the particle size. And what you certainly find is that as you rotate the wall, as you keep going, because the dilation angle is changing, so that the shear band tends to sort of wander around and tends to thicken a bit. So it's not an easy task to get an exact number for this ratio of particle size to shear band thickness. But if you look in the literature, then you find that typically, and here are various different cases down here, the different gradings of the sand, particle size, rupture thickness, and the ratio of these two numbers here is of the order of, well, 10 to 20, I should say, for most cases. These are ones we did in Cambridge. This is Martelakis and Mulhouse in Karlsruhe. So, intermediate scale of 2, this is the thickness of this shear band, or dilation band, and it's typically of the order of 10 to 20 times the particle size. And there's a question here, too. How much density change do you need to be able to detect with X-rays the boundaries of this band? And if you look back at the picture here, I mean, you will see there are definitely bands in these various locations, but where do you put the boundary of the band in this region here? It's sort of going from white to dark grey, but the boundary in here is quite difficult to determine. So there's a bit of subjectivity in picking that boundary. But so there's intermediate scale 2. Right. The next one is a bit more subtle. It's localization of something or other in the presence of shear. And one of the messages that I want to try and bring out throughout this talk is the importance of shearing, rotation of principal axes, which is something that we tend to ignore, we tend to overlook in much of the testing that we do in the laboratory. And yet it's very, very important, because we know that we can see that the instabilities in soil behavior are often triggered by rotation of principal axes, and we'll see that in due course. So let's look at these localizations in presence of shear. And there are several cases we will look at here. One is it's a sort of a foundation settlement problem, but it's not a trapdoor problem. It's more a matter of discontinuity of slope. So there's a change in slope here, but not displacement. So there's continuity of displacement, but discontinuity in slope. So there's shearing going on. It's rather like you've got a sort of shear vertical shearing of the material. Rotating a blade, obviously, again, is a shearing process. You're making the saw go over sideways. And here's a more elaborate one where there's a floating blade where it can be moving left and right in active and passive conditions. And simple shear itself, where you have a shearing sample that is just moving relative to the top, relative to the bottom. And these are all cases where you have rotation of an intention of trying to apply shear stresses and develop something happening in the presence of shear deformations. Well, let's look and see what we can get. These are radiographic pictures of a model of a sand deposit with this rotating boundary at the bottom. So this is rotated from horizontal down to that value there. You can see the different cases for the different sizes of sand. This is fine sand. That's fine sand, medium sand, coarse sand. And if you look at these things, you can see with radiography a pattern of dilation bands. I've called them dilation bands because that's what they are. And you can see that as the particle size changes, so you get a more elaborate condition of the patterns of these bands. And for the coarser materials, you actually see a crisscross network of bands rather than simply a series going off in one direction. But these are then dilation bands seen in the presence of shearing, in this case, the sort of vertical up and down shearing of this material. Those are seen with radiography. So those are on the inside of the sample. And if we look on the boundary of the sample, so the front edge of the sample, which you can see, then you find that you get evidence of stepped. We have marker bands there. You can see there's steps in these bands, and we can pick those up as indications of something happening inside the sample. They don't necessarily reach the boundary, but they're certainly present on the face, the visible face of this plane strain material. So that, there are various different classes of localization occurring in this material. So that's localization in the presence of shear. Then the next one is a nice one that we call spontaneous regular volumetric heterogenization, if you get your tongue around that lot. And what it is this. Here is a floating blade. It's a wall which is allowed to move, well, it's moving forwards and backwards. And if you have the eye of faith, which I hope we all have here, you can see that there's a wall there, or blade here, going from there down to the bottom. It's rotating into the soil. It's rotating into the soil in this region here. And you can see that there are sort of major dilation bands down like that. There's also some information here. There's some little bands there in both directions. And if you look in this region here where the blade is moving away from the soil, so you get active conditions here, there's clearly sort of, you can see this grid of dilation bands forming in front of, or beside the wall there. So we have a range of different patterns of these dilation bands occurring around this floating blade in the soil. Now, eye of faith, as I say, let's just go to that is my interpretation of these bands. So you see, it's really quite a detailed pattern of bands. It's not just one curve like this one here. It's actually a series of bands forming a sort of parallelogramic structure through the sand. So this is spontaneous regular volumetric heterogenization because it seems to happen rather suddenly. And it's regular. You can see these regular cells here. It is. Sorry, that's very good. Yes, it seems to happen quite suddenly. It's definitely a volumetric effect, and it is heterogenization because actually it is turning the soil into a non-uniform material. So radiography picks up density contrasts, and our interest in terms of trying to pick up a intermediate scale is to say what is the size of this typical unit of this reticulation, this network of dilation bands. And what are they anyway? Well, perhaps. I don't know, perhaps they have an intersection angle of about 65 degrees. So perhaps they are sort of Roscoe's kinematically constrained dilation bands for which the intersection angle should be something like 90 minus the angle of dilation, 25 degrees, and that seems to fit in quite nicely with the number we see. So here's a third intermediate scale. The scale is the size of this network here, the size of these cells here. So it's not just the thickness of the shear band, but actually the size of this elemental network of this regular volumetric heterogenization. And that's something which is quite a lot bigger than the size of the cell, of the shear band itself. This is what we missed out with the previous picture. So it's, what we're seeing here is observed in the presence of imposed shearing. Most of the studies of shear banding have concentrated on tested fixed principal axes, triaxial and biaxial. And so if you do that, you miss out on the important range of observations you can make in cases where you have rotation of principal axes. At the time when I made this slide, and you see I was in Bristol at that stage, we had a mathematical study going on. We were trying to find what were the constitutive characteristics conducive to regular bifurcation. So the question is, what is it you have to have in terms of your material response, your description, which will tend to give you this sort of form of result as you have a rotating wall? And we didn't really clarify the answer to that one, so that's still an open question. How do you generate the model which actually will generate this sort of patterning of volumetric change? So that's an open question for the bright members of the audience here. So, patterning, intermediate scales. We're getting the dilation bands from radiographs, and if you have, so long as you have the eye of faith, you can see there's quite a lot of richness to this. You can see the regions up here of white density change, and there in front of the wall too. Spontaneous regular volumetric heteronization. So the scales, what are they? The band thickness, we know that's about 20 times the particle size. Band spacing, which is the spacing of these parallelograms here. And the question is, what are the necessary quantitative characteristics we need to have for those results? So that's another intermediate scale coming in. The next thing to look at is then a particular testing device which they have at Grenoble, which is called a directional shear cell, and we'll see what we can see from that one as indication of really quite interesting features of the non-uniformity, the heteronization of this material, a material. So directional shear cell, they actually call it 1 gamma 2 epsilon, and it's the notion is this: we have essentially a rectangular sample, quite big, 0.5 meter by 0.5 meter roughly. So there's a big sample here, and all these bits around the edge here allow it to deform in plane strain, but with the length of all the sides changing potentially and also rotating. So you go from this solid green rectangle to the dotted green parallelogram quite happily, with the sides changing in length and the angles remaining constant. When I first saw this device, it was made out of Lego back in 1960, 1970, something like that, and they subsequently made it into metal, so it's sort of subsequently able to cope with real soils. But it's amazing what you can do with Lego if you have it in your pockets to make these sort of apparatus. So this is it's a plain device. It's not for testing real soils. It's for testing granular materials, which are in this case rod materials. And the notion is that you can apply all the strains that you want to for a plain test. You can apply 2 direct strains, left horizontal and vertical, and also a shear strain, this rotation of these boundaries. So it's a plane stress loading, and we did it with 3 sizes of plastic rods. So it's a sort of proto-granular material, and there's the particle size distribution. So here's diameter on a logarithmic scale, and the percentage finer, as in the usual way. So we have 1, 2, 3 particle sizes. So it's what the Europeans call a Schnabeli material, which has this rod. It's simply rods actually, made out of PVC, but they call it Schnabeli. So that's the material, and you fill this huge space here, 0.5 meter by 0.5 meter, with these rods in a random way, and then do the tests. And a typical test is one like this with isotropic loading up to a stress of 50 kilopascals. Then a test with one test kept constant, one stress kept constant, and the other one increased with fixed principal axes, and then fully strain controlled tests on this material, following a linear strain path in the to the direct strains and the shear strain plane. So that here is the typical test. So we have here, this is volumetric strain and general shear strain. So it's the straight path in terms of dilation, so that you have these different angles going off here. So these series of tests, all at a constant slope, so constant incremental ratio in the ratio of volumetric strain to shear strain. The principal axes are going to be fixed too, so here is as you go along a line like this, the ratio of the shear strain to the sort of difference between the X and Y strains is constant. This controls the principal axis direction of the strain increments that are imposed. So it's imposed strain paths, fixed variable principal axis direction, and fixed but variable dilation rate for different tests. So it's quite a sophisticated device. And these are rods that we're testing, not soil. And there we have the shear stress, normalized shear stress on the vertical axis against this stress difference on the horizontal axis. And you can see the paths followed, and these arrows indicate the the strain increment directions, and you can see that eventually you end up with more or less radial strain increment directions on this circle here, which essentially is a Muir Wood failure circle, constant friction, out there in this plot. So you end up with a sort of normality to the Muir Wood circle in this particular version of the stress space. So that's the test being taken along these various paths. What happens? Well, the key thing here is that what happens is this, that although you've got a uniform sample, let's say you've got the boundaries of the sample are straight, and they're simply rotating and extending, whatever. So they're rigid boundaries. They're not flexible at all. And yet, when you start doing the test, almost immediately you find you get a non-uniformity of deformation. This is volumetric strains in this picture here, and you can see that there are huge variations in the volumetric strain, variations across the sample, very quickly, almost a zero strain. So you can say, looking at this, that although the boundary displacements are homogeneous, the natural state appears to be a heterogeneous state, in the sense that you're not looking at a uniform sample. There's a range of volumetric strains across this material. So what is the size of the representative element? Do you need to have a sample half a meter by half a meter? Clearly you can't have something which is that size, because if you had something in there, it's got no variation at all. So actually you have to have something bigger than that. So you look at this and you say, how far back do I have to go in order to say this is a representative state? Difficult to say. But just to show more of this information, here is the distortional strain on the bottom diagram and the volumetric strain on the top diagram, the same picture we've just seen, and you can see perhaps more clearly here the structure of these variations of the different strains in the different cases for the different parts of the test. So the test is being run with constant dilation, run with constant principal strain directions, and yet inside it's doing this. It's not a single element at all. It's a mishmash of different strain components. Well, I won't go into this, but one can pick off the features, one can pick off the orientations and try and look at the orientations in relation to the overall externally imposed stress state, and try and see whether you're looking at Coulomb, let's say, stress controlled orientations, or Roscoe, kinematically controlled, to see whether they fit in with either of these pictures. And the answer is that there's something in between these two. There's a mixture of the two various different constraints. And we can look at the way in which these localizations, these localizations of deformation occur either on cumulative images. So this is looking at 0.41 to 1%, 0.41 to 1.6. So this is cumulative, going from 1, 2, 3, 4, 5, 6. And at that stage, you've got pretty well a diffuse localization across the whole sample. But you can see how you're building up the appearance of these features across the various different images. That's on a cumulative basis. And here's the same thing seen on a incremental basis. So here you see this is 0.41 to 1, 1.1 to 1.6, 1.6 to 2.1, and so on. These are incremental stages during the test. So you can try to analyze the formation of these features in terms either of the incremental behavior or the cumulative behavior of the material. But all the time we're looking at an overall sample behavior which actually is uniform. There's the rigid boundaries. There are no variations there as far as we know. Well, so picking off these again, this is the incremental behavior. We can pick off the spacings and the orientations of these possibly parallel features, and to try and say what is the size of the unit cell for this material. And these are histograms showing the dominant spacing as to being about 3.5 times 50 pixels. So something like 11D50, this number here, and this is the sequence in which they occur. So you can do some statistics on the size and the nature of these features that occur within this material. And close to, well, it's not. You can see that now we haven't got a continuous localization, but we have a splodgy effect. You look at try and get the size of that, the spacing of that. These are obviously rather empirical, rather sort of approximate features, but there are numbers that we can pick out for this two-dimensional rod material. So it's not a three-dimensional material, it's a two-dimensional material that we're looking at in this case. And for a two-dimensional material, you tend to get much smaller numbers than you do for a three-dimensional material. So 10 for D50 and 10 for the spacing and 2.8 for the thickness. Well, they're about right. Okay, that's talked about directional shear cell, and the next thing to do is talk about photoelasticity, because we're trying to find some way in which we can see inside the soil. And we can't obviously see inside the soil in general, but we can find some analog way of getting an indication of what happens inside a granular material. So here we're looking at classic results by Andrew Drescher of the behavior of photoelastic disks under sort of crunching shear. So it's against another example of the particle continuum duality. And it seems to me interesting that these were tests done in 1972 in Delft, and really it seems to me that the people doing computing work on discrete element modeling have revealed nothing that we didn't see in those tests of Drescher's in 1972. In that what we're seeing here is the key thing, that actually you have these chains of particles which are carrying the load. These dark chains here indicate the load being carried through the material, and some of these particles have no load in them at all. These ones just here are just filling up space and not doing anything in terms of supporting the load. So this is an important result which actually has been confirmed but not actually exceeded by the work subsequently in the DM studies. And I think that I understand that from Andrew Drescher, this is his most quoted paper. It's a fantastic bit of work for that period. Well, how do we see them? Look, you've probably seen these things yourself. We cannot see stress within a mass of sand because it's an opaque material. But if we use a surrogate granular material and the principle of photoelasticity, then we can see something of some effects. And if you have a disk, there's a disk of glass seen in white light. The material changes, the refractive index changes under stress, and it changes by an amount depending on the principal stress difference. And so that these colors here indicate the local value of the principal stress difference for that material. So that this two-dimensional material, it's just a disk. You have uniform stress through the thickness of the disk, and we can look at that and see what are the stress differences, what is the stress level for this particular disk at any point along through this material. So it's rather a powerful way of looking at the stresses within a element of a granular material. And here we can see disk being gradually loaded. So here's the unloaded disk on the left. We apply diametral loads, and so we start getting a brightness here where we see the stress increasing. This gradually fills the disk, and then you start getting another little dark zone coming in, and so you see this dark zone building up, and you can see that as you increase the load, so that the pattern becomes more complex. But you can look at the number of fringes here from the free surface to the point of loading, and use that to estimate what is the stress difference in the material. So it's disk under increasing diametral loading. We've, in this case, viewed with monochrome polarized light, and the fringes show the local stress intensity within the disk. And you can see here that because of the way in which the fringes form, the relationship between stress and light intensity is not actually monotonic. So that's a detail about the way in which you might interpret the results. So if you go back to Drescher's pictures, you can see there are various different cases. Here there are particles which have no stress in them at all. So there's zero stress in these particles. Obviously in the void between the particles there's no stress either, so that's zero stress in the void. And even in one of these loads, in one of these particles with a very heavy load on it, there's an unloaded edge, so there's no stress there either. So there are three cases of no stress: edge of particles, some particles no stress at all, and the voids. And some particles have very high stresses at their particle contact. So we have a huge range of these things. So evidently, pretty obviously, the concept of stress has no meaning at the particle scale. It makes no sense to talk about particle stress scale. The actual value varies extremely with the location of the section and the test area. So whatever, you can pick a number and that number there, or pick a space there, and you get a quite different value of stress, actual stress, from place to place. What do we mean by stress in a particulate material? It's one of those naive questions that you can ask. And when I was the examiner for Jelke Dijkstra in Delft, my first question to him was, what is stress? But you can see where I was coming from, and actually got quite a long way through this argument here before he stopped. So, I mean, photoelastic stress just under shear, these are two black boundaries here. You could scratch them together and look at the way in which these stresses changed, these paths of loading change through the material. And you can see here that you can pick up on the right-hand side, these lines here represent the stress, the magnitude of stress between the particles, and the thicker the line, the bigger the stress. So you can see here, this is just the same indication as this one, where it's a similar location to this one here. And some of the particles have no stress, and some of them have very high stress. And you can look at this and you can say, well, actually, if I stand back far enough, it looks as though there's a network of stresses there too, just in the same way as we had with the strains, perhaps. But you could say that there's a series of patterns like this with a size of the order of 5 to 10 times the particle size. I mean, that's my estimate of this. So if you look at this ring here, about 5 particles. So typically, we're seeing a series of rings of particles, groups of particles which actually have the order of 5 to 10 particles as a dimension of those groups. So if we wanted to pick another intermediate scale, then 5 particle sizes might be the right number to use. So as you get further out, so the fabric appears increasingly homogeneous as the scale increases. A typical network mesh size might be the order of 5 to 10 d50. How big do you want to make that? How big do you want to have your samples as to be uniform on the particle scale? Well, you probably want to have about 50 to 100 times the typical size of the mesh. You want to have some number of these units. I've said about 10 here, actually, which maybe is too small, because you want to have more than that, perhaps. But you want to get out to a level that you have homogeneous heterogeneity. So the question is, how small an element can appear homogeneous? Pseudo-homogeneity requires observations at a scale large by comparison with dimensions and patterns of heterogeneity. So you've got to come far enough away that actually you can pick a number which is big by comparison with the size of these individual nets, in this case. So there's the result we're looking for. One of the things we see in these tests is there are these loaded chains of particles through the material. Typical, these large numbers here, and the thick lines indicate the big stresses. And they're quite stable so long as the stresses so long as the principal stresses don't change in direction. So long as you're just sort of pushing straight down, then you can keep on increasing the load and they will be very stable. But if you change the direction of the load, if you shear them, if you apply shear stress, then they collapse. So you have here these columns of particles transmitting forces, which are very sensitive to buckling under shear. So these side particles are trying to hold them together, but if you change the rotation, if you change the principal stress direction, they collapse really quickly. So this is why I say we should be concentrating more than we do on the behavior of materials, of soils in conditions of shearing, simple shear, rotation of axes, rather than the fixed direction of the stresses in traction apparatus, for example. So fixed principal axis testing explores a very, very limited and rather stable region of response. If all you're doing is just simply increasing the stresses again and again and again in one direction, you're not really testing the sample in its sensitivity to the shearing process, which will certainly be very disruptive. So I'm just repeating these things, but actually just to remember over again. We see these columns of particles carrying major principal stress. This is DM work, this is numerical work, and it's essentially showing the same results as Drescher showed. The neighbouring lightly loaded particles help resist the buckling, but rotational principal stresses, so that shearing is definitely stabilising. It's a neglected area of laboratory testing. And we need it because we're going to be applying our constitutive models in this area. And we're not looking at we need to allow for the fact that the prototype stress paths are not constrained to have fixed principal axes. So we definitely should look at these rotational axes as being part of our test program. So, rotation of axes is desperately important, and we don't give it enough attention. So then, just sort of summarising this Drescher work, particles are born free and everywhere in chains. And here is our intermediate scale 5, which is somehow to do the network of these particles, these rings of particles in a system like this. So again, can we pick out a scale in relation to particle size? Now it's worthwhile noting that those were tests on disks, photoelastic disks, but you can see the same thing with photoelastic particles, and also that's a more realistic soil analog. And this is a soil well, it's not it's a glass grain, it's 1 millimeter glass sphere, being held within these pliers, these teeth, which are being gradually jacked together so to increase the stresses. And you can see on these bottom pictures here, this is 1 millimeter stress, 1 millimeter sphere, so it's very small. But here's the change in the light coming through that bead as we increase the stresses across the boundary here. Now, in order to do this, we have to put the bead in an immersion bath, and you see it says there immersion bath. We were using in Poland clove oil, and these are the nicest smelling experiments I've ever done, because clove oil is actually a rather nice sort of smell to use, but it has the same refractive index as the glass, so you can look straight through the clove oil and through the glass bead and see the effect of the stress state in the bead on the polarized light that's going through it. So I commend to you the idea of doing photoelastic tests on glass using clove oil as the refractive index medium. So those are beads now. These are not discs. These are actually spheres under diametral loading. And this is then an attempt I've made to reproduce the way in which the ray passes through these spheres. Because now if you have a sphere which is being subjected to diametral load like that, then every point in the sphere has a different stress state. So there's no one stress state for the whole sphere. You have to look at them. The ray of light comes through. It'll go through many different, well, an infinite number of different stress states as it goes from one side to the other side. I've done the sums here with 25, you see the squares here, 25 steps in each direction. Not enough, but you can see how the stress state, because the stress state varies from the outside to the inside, you have a very different variation on the polarization as the ray goes through, depending on whereabouts you are. So here is my reconstruction of the stress state in a sphere, a glass sphere under diametral loading. So it's quite a challenging problem. If you then have a real granular material, you have one sphere here, you have the spheres all over the place. So any light ray coming through that will be going through a hugely randomly varying range of stress states within each sphere and within the spheres in the layers. So it's a very random problem you have to analyze. Here are the typical spherical particles of 1 millimeter diameter, but we can also see with crushed glass, you can see again even with those that actually you can see these dark bands forming near the point of contact as the load increases. So there's a sort of indication here of the increase in stress level in that crushed glass bit as the stress is increasing. And just a note about strains. Obviously, we can't define stress, we can't define strain either, because the strains that we see in soils are actually to do with the movement of particles more than about the deformation of particles. The strains in the particles themselves are very small, negligible really, and all the movement that we see in the soil is to do with the particles, the particles moving themselves, and you can see the change in displacement gives an indication of the strain of the overall behavior of the overall material, but not a strain of the particles. So just as we can't define stress, we can't define strain either in a useful way locally. So just summarizing, this is the Osterberg, de Jong and Drescher stuff. Photoelastic disks, forced chains, fabric, particle locations, low contacts. Some particles carry no load, some particles carry lots of load, and we're seeing this distribution, which is something which is picked up by the DEM work, and really just showing the same thing over again. So now then, implications for testing, and I'll just draw a few conundrums here for the material. The first one is this. These are the typical pictures. If you look in Taylor's book from 1948, then this is the classic pictures of dense and loose triaxial response. If you have a dense sample, then you tend to get this shear plane forming. A loose sample, you tend to get this bulging forming. The bulging we say is good because it maintains the axial symmetry of the deformation of the sample. It may be bulging in the middle, but actually it's still circularly symmetric. Obviously, the failure plane is actually breaking the symmetry of the sample, and it's giving us a deformation across in one direction, particularly through the material. That sounds very easy and very nice, but actually more recently, Jacques Desroux in Grenoble has been doing some fantastic work looking at what happens inside soil samples. And these are pictures which he produced in 1996. These are Hoston sand, the sort of European sand, And these are volumetric strains. So the color indicates the intensity of volumetric strain in the material. This is just a standard triaxial sample. So there's nothing special about this. And these are the volumetric strains seen inside that sample. And as you go through, you can see that he interprets those pictures as indications of sections through. These were horizontal sections through the sample. They're sections through the sample, and he sees those as being evidence of sections through some really quite complicated mechanisms. So you see here these sort of little dormer windows, as it were, these sort of various different orientations of planes, and this conical arrangement here. There are really very subtle deformation mechanisms occurring within the sample of this sand. It's not behaving axially symmetrically. These are not, these little things, these chaps here, they're not axially symmetric, they're locally straight, flat, planar systems. So to look inside this sample and say we have a microcosmic simple triaxial sample occurring inside this bigger sample is completely in error. That's volumetric strains, and what he found there was that looking at the void ratio, either globally or locally, against axial strain, the solid symbols indicate the strains within the shear bands or the dilation bands, whatever, and you can see that those reach this final critical state value very rapidly, whereas the global values never get there. They just sort of tend to sort of hive off to the side here. So it's clear, it's not surprising actually, the main deformations are occurring within those mechanisms. So that's the volumetric behavior. More recently, he's had some pictures done with computerized topography of distortional behavior, and this is a triaxial sample. What's happening? Any other ideas? The behavior is completely different from it's not. There's nothing actually symmetrical about that at all. There are two pictures of a similar result, but you can see that these features. These are the incremental deviated toric strains. So the variation of color indicates variation of magnitude. Well, I don't know what it is. What we can say here, what we've done all through this lecture is look at the behavior in plane strain or plane stress situations. And for all those situations, you can say that what we see locally is essentially a small version of what we've imposed externally. But for this triaxial sample, there's no link at all between what we see in this internal picture and the external behavior. So it's something which is quite different. There's a behavior in the soil which is trying to catch up with whatever you're doing externally, and it can't cope. It can't keep up with the axisymmetric stress. It's showing deformations there which are something quite different. Now I'll show you one more picture of another stress device, which may be a more useful one to look at. When Ken Roscoe, again I mentioned him before, when he was setting up his research at Cambridge in the 40s, he decided that the triaxial was a bad test to use. Well, he's pretty right there. And he wanted to produce a simple shear device, which he reckoned was going to be a more suitable test to use for looking at soil behavior. And he spent the next 25 years, until he was killed in a car crash in 1970, trying to produce the ideal simple shear apparatus. What is ironic is that actually there are two things he despised. One was the simple shear apparatus. One was the triaxial apparatus. The other was Imperial College. And the key paper that Roscoe, Skiff and Rose published in 1958 on the yielding of solids was all based on triaxial stress data from Imperial College. So the things that he excoriated mostly, he made use of in that paper. So, well, this is a fancy shear box, a simple shear device produced by Allersma in Delft in 1982. And it's a quite clever device in which you've got the soil here consists of crushed glass, because this is a photoelastic situation. So the crushed glass is in this caterpillar track here, rather like the caterpillar track on a construction vehicle. And this, then you pull this the bottom sideways, so it's got teeth along the bottom. So as you pull it sideways, it is pulling the caterpillar track around, and the middle part of this material here is being given a continuously reorienting simple shear deformation. So a normal load on here, and this is then a very good continuous shearing device. This is 1982, and amazingly for 1982, he was able to do various things. Because he's looking at crushed glass, he can look at that with polarized light and deduce the stress state in the material. So although there are no stresses in the soil, he was able to deduce the stress within this crushed glass. You can see also here these dots here indicate the lead shot that he's using to look at the deformations in this sample. So again, 1982, before the photography in PIV, whatever, he was looking at the displacements and working out the strains at different points within the sample. And he was deducing, back in 1982, a long time ago, the non-coaxiality of the strain influence and stress from polarized light photoelasticity for the stresses and this direct movement of the lead shot for the strains. So really pioneering work. And this is a device which actually I think would merit being rediscovered, reused, because actually it's such a useful device for looking at stresses and strains within the soil sample. Well, that's crushed glass and some implications for testing. And so I end up with some conclusions, which are going to be intermediate scales. What happens inside the soil? Is the laboratory test a single element? No. We have to contrast the system and the elements. And the system is really what we see at the sort of big scale, and the element is what we see at a small scale. We have to be aware of this standard research fact that absence of evidence is not the same as evidence of absence. They're quite different things. So in fact, we don't see something, and this last statement here, it is tempting to assume that things that we choose not to observe do not exist, which of course is one of these things of research. We must remember that because we don't measure them, doesn't mean they're not there. So what happens inside the soil? And I've tried to show you by looking at the deformations and looking at the stresses for the photoelastic case, ways in which we can pick up something about the way in which the soil is behaving. And in summary, here are our series of intermediate scales that we've looked at, we've discovered in our testing. The first one is this development length at the end of a shear band, perhaps 100 to 200 times D50, which allows us to get reduction of the latency to critical state. Then the second one was this thickness of dilation bands, 10 to 50, 10 to 20 D50 seems to be a typical number, but no one's really tackled the answer to the question of what happens when we have well-graded soils. All our tests have been done with single-size materials, and obviously then with well-graded soils we have something different happening. We don't know what. Then we have this idea about the patterns of spontaneous volumetric heterogenization. The cell size perhaps is 30 D50. If we're trying to find a representative size of sample which is big enough to hold a random number of those cells, at least 10 presumably, which would give us something like 300 D50 as being a typical sample size. We've seen patterns of internal inhomogeneity in two-dimensional granular material. And the Drescher work on particle assemblies showed force chains defining similar cells. So here's the last question. What is the dimensional sample or model in order to smear out internal inhomogeneity? And that's over to you to answer that question. Answer on a postcard, please, by tomorrow. Thank you very much.
Very, very much, David. That was wonderful. I think one of the great things about having David around is if you're curious about somebody, whether somebody's done this before or not, David's the man to ask. And it turns out there's a lot that people have done before, and it has gone sort of underappreciated. Also, you get a sense of how much work there is to do with granular materials and soils. And I'm reminded of something that Paul and I discussed. I think you quoted somebody saying, don't even go here, it's a black hole. So I guess the conclusions that you leave is, it's a black hole. It sucks up your career, if nothing else, or in a glorious way. I think we're in agreement here, some of us. So with that, are there any questions? And I would pass around the microphone because we are recording this. We don't know how well we're picking everything up, but we'll try to do it by passing around the microphone. Any questions, Giuseppe?
David, thank you so much. Very, very nice and thought-provoking presentation. I was curious about the definition itself of the concept of development length that you showed, and because in its conceptual scheme, it's something that is shown with reference to a slip surface that has already fully formed. And the way I think conceptually to the formation of a slip surface is more of a gradual process. And I'm thinking, if I have in mind this gradual process, should one think of the mobilization length as the minimum length at which the first point at which the bend is triggered has achieved the fully softened strength, or more of a characteristic length over which all points are already at full residual strength?
With the X-ray system, you can actually pick up, although with the X-ray system looking at the movement of lead shot, you can pick up movements occurring around the region where you subsequently see a shear band or inversion band, and so that you can investigate. You are measuring deformation, displacement strains in this region here, volumetric strains in this region here, even though you can't see the shear band there. So you can see, you can detect from the overall field of deformations where is the maximum dilation occurring, and that's an indication of the fact that a shear band is likely to form there pretty soon. So that you can deduce where that is, and this is obviously then this is the shear band which has formed. So you can see this, you know where this is, and you're seeing this by deduction as being the future area here. So I think the information is there to be able to take this out. It's much less clear, I think, that there is a number. We've chosen 150. Lux, I think, took about 120 or something, but the people have tried to look at it. But it's not clear that it's actually such a fixed value.
Yeah. And I had another question related with these very classic scalings of certain geometric features. It could be the thickness of the shear band, or in this case, this mobilization length. And they scale with some geometric parameter of the granular material, let's say the grain size. In this schematic, however, you were showing that, I mean, rightly so, the characteristic strain at which the material fully softens depends on the distance between the peak and the residual, and thereby density. And I was wondering, does the density, so the state in addition to the grain size geometry, plays a role on modulating these lengths, both the thickness or the mobilization length?
It's strain. There's no strain of it. It's not a strain of it.
Yeah.
It's displacement control.
Yeah, yeah.
It's the length over which the displacement. That's what I don't know. I mean, it is a displacement change you're looking at.
Other questions? I excluded forgot some biographical details when I was introducing David, and one of the things he said at the beginning was no tough questions, so feel free to ask anything technical or philosophical. Actually, the philosophical ones are just as good. Well, I'll ask my questions then. I think one philosophical question I may ask momentarily, but technically the Schnabeli materials that you talk about, that you've discussed here, have always been a curiosity to me because they faithfully are a two-dimensional representation, which we often just gloss over. We think about running DEM simulations and interpreting them in a 2D sense, or pretending that we have 2D discrete element simulations, and then we try to interpret the results as meaningfully applying the 3D materials. So do you have any thoughts on this, the Schnabeli materials, both in the DEM world and in the experimental world? Is the information that's extracted from this, which is arguably a kind of a contrived situation, is it useful generally as a model for soils? Or maybe to put it the other way, is it the right way to be doing the interpretation, since it is a proper two-dimensional representation of what is otherwise a three-dimensional problem? If that's a...
The advantage of the rod material is that actually you can look at the rotation of individual rods. You get a lot of information about every particle in the system, and then every particle goes right the way through from one face to the other face. There's no boundaries there. With any realistic material, you've always got many particles between the front boundary and the back boundary. So it's much harder to pick up the individual rotations. But I think one's going in steps, and one's saying, well, okay, let's look and see what we can do with rods material as a proto-granular material, and then gradually increase our confidence as we look at particular material.
Any other questions from the audience? Yeah.
Thank you, Professor Wood. It's a very nice lecture. So in terms of the scaling and if you look at the sample from different point of view, you see different picture. For example, a traction sample, if you see from the global measurement, you think this may be represent a elemental stress strain response, but you show the picture, actually there's a heterogeneity within the sample. So stress field is very different with, if you look at the microscopic scale. So I'm wondering, like, if we treat the tracker sample as the scale, like, so I can use the global measurement as the my elemental stress strain response, right? So does this imply if I use my data from the lab, then if I go to FEM to do the modeling, I need to select my elemental size, which comparable with my size of the sample?
I think the triaxial sample test is a disaster, actually. Because I think because if you think about what you're doing, you impose a vertical movement, you impose a radial stress. Those are the only constraints you have, so, and everything else is free for the sample to do what it wants to. I think that it seems to me what's happening is that there are a series of mechanisms, perhaps shear mechanisms, in different orientations, which are somehow combining to give you an overall, roughly symmetric response. But we don't know because we don't measure them. We can't measure them. But I think that it seems to me that given these pictures, that there's no obvious way in which there's an elemental behavior which is. I can't see anything from there which actually looks to me like an axisymmetric element. Can you? It's just, you know, it's something quite different. Very nice, beautiful, but it's not axial symmetry. It's held a skelter of ski. That's what ski lift.
But I mean, what would be your suggestion if some people give you the lab result from the traction cell? How would you use this data to fit into the constituent model, or use the data to do some simulation, FEM simulation for, let's say, a real geotechnical application, a foundation or excavation, if I cannot assume this is an elemental response? Or
I think I think the elemental response is probably a simple shear mechanism, and I think if you probably somehow link those together for a sample like this, you might be able to produce the overall response. But I think that what I'm trying to say is that the elemental mechanism is actually quite different from what you see here, and quite different from the overall axisymmetric response too. But I think beyond that, you open the window and you try to go outside.
So I think the answer is simpler is better, is it?
Probably, yes. Yeah.
Probably. If there aren't any other questions.
Yes.
David, I really appreciated your presentation. The focus on scale is a very important one, I think, that we all need to pay a lot more attention to. But I was curious, what are your thoughts about clay? I mean, sand's complicated, but what would you do about clay?
When I was
not that you can answer that in less than 25 years.
When I was a boy, I played with clay. And so all my PhD work was on clay. And then as I grew old, I became impatient because clay takes a long time to do tests. Tests take several months to perform. And with sand, you do a test in half an afternoon, so it's actually very quick. And clay is messy too, actually. There's a nice, I can't remember it all, but a nice Hilaire Belloc poem about his uncle came on Frankenstein playing in the mud. He's not very happy because it's messy, but he says, nice boys can always play with sand, actually. So that's why I've been playing with sand. To answer your question, well, okay. I think we don't know, actually. I mean, people have not done this sort of test, this sort of operation in clay samples. And it'd be interesting to see what they do see, because it may be that in clay you've got a much more, the sample, the particle size is smaller, and maybe there's more of a smoothing out of the differences we see here. I don't know the answer to that, but I mean, it's something which is obviously, it's a very perfectly valid question to ask, actually. And I shall pursue it.
There wasn't another question that came up. I'm dying to ask, do you agree whether or not it's a black hole? And I guess maybe to sharpen that, will we ever resolve this complexity and these questions that come up here? And is it worthwhile to resolve them in the same spirit of what Jinhao and Chuck asked?
When I gave a lecture in Oslo some years ago, I called it The Magic of Sands, which is a quote from Saint-Exupéry, when he says, "Nous ne sommes nourris de la magie des sables." We are nourished by the magic of sands. And I had to challenge myself. I wanted to find the origin of this quote from him. And so I looked on the web and found that there were two possible books that it might have appeared in French. And one was very long and philosophical, the other one was very short. And it was in the short one. The curiosity was that in the English translation it had disappeared. They obviously not neglected that bit of the English translation of the book. The moral there was, don't believe everything you read on the web. Because if you believed that it was in one of these things, you'd have given the wrong reference completely. And if you give it an English reference, you'd give it completely wrong because it wasn't there at all. But he was contrasting the people who were nourished by the magic of sands with those people who built oil wells and sort of generally despoiled the desert in North Africa. So he had an amazing time flying to and fro across North Africa and eventually crashed there and was rescued by Bedouins. But he was a fantastic airman. But why was that? It's not a black hole. It's actually it's a challenge. It's a magic challenge to try and dig out the truth from this material. Black hole sounds too negative. We don't have negative statements.